In this first section, we're going to discuss something known as collision theory. We're going to start by looking at a couple of different types of reactions. Let's first look at a reaction that happens very fast, like the reaction required to inflate an airbag in the case of an automobile accident. When a collision occurs, there's an electric charge triggered by that collision that starts the reaction in the airbag, where sodium azide, solid, which you see here, is converted to nitrogen gas, which you see here, in 0.030 seconds. So that has to happen very quickly so that gas inflates the airbag quickly for passenger protection. Some reactions happen much more slowly. So to contrast the one on the previous slide of the airbag, when a metal structure rusts, you can see these nails here with rust forming on them, the reaction is very slow. It does happen, but it happens much more slowly and continues on for years. This process of iron, metal reacting with the oxygen in the air to produce the iron oxide rust that you see forming on the outside of the nails. So these rates at which reactions occur, the speed with which the airbag reaction occurs, or how slow the rusting reaction occurs, is the basis of kinetics. So in kinetics, we study the rate at which a chemical reaction occurs. Rate is, in general, a measurement of change over time. So this is what we have to remember, is that we're discussing change over time. We're going to be looking at this idea of change over time quite a lot, especially as we get into some graphical analysis and calculation. So something to keep in mind. Kinetics, so we're talking about a rate, right? So change over time. In specific, kinetics measures the change in concentration of reactants and products over time. So we're talking about the concentration over time. A chemical reaction involves a change in the arrangements of atoms and a change in their chemical bonds, right? The atoms in a molecule break apart and rearrange themselves to form products. In order for atoms or molecules to react with one another, though, they have to collide with one another. The theory that describes how reactions happen at a particle level is known as collision theory. All right, so here are the basics about collision theory. In order for a reaction to occur, two things must happen. The particles must collide with two things. One, enough energy, and the proper orientation. If the particles never collide, never come in contact with each other, there won't be a reaction. If they do collide, but they don't have enough energy, they have less than the minimum energy required, there won't be a reaction. If they have enough energy, but not with proper orientation, there won't be a reaction. So they have to collide with both enough energy and the proper orientation. The more frequently that happens, the more frequently particles collide with at least the minimum required amount of energy and the proper orientation, the faster the reaction will occur. Here are the factors that help ensure that more collisions have the minimum required energy and proper orientation. Physical state of the reactants, concentration of the reactants, surface area of solid reactants, temperature, and the presence of a catalyst. We'll discuss each of these in more detail in the following slides. Each of the factors listed on the previous slide can be manipulated to make a reaction proceed more quickly. Each one impacts either the frequency of the collisions, the energy of the collisions, or the orientation of the collisions. For example, increasing the concentration of reactants will increase how often collisions occur, while increasing the temperature will increase the number of collisions that have at least the minimum required amount of energy. These factors and how they impact reaction rate will be discussed in the following slides. The first factor we'll discuss is the physical state of the reactants. Reactants which are gaseous collide more frequently than reactants which are liquids or solids, because their particles are moving more rapidly. Liquid or aqueous particles will collide more frequently than particles of solids, but not as frequently as gas particles. Since solid particles are locked into place, they cannot collide, so two solids will very rarely react. If one reactant is a solid, the particles of the other reactant or reactants must migrate to the surface of the solid to collide with the solid's particles. If a reaction involves only solid reactants, for example, the decomposition of solid ammonium nitrate, high temperatures are required for the reaction to occur. The high temperature melts and then vaporizes the solid. So the reaction in that case actually takes place in the gaseous state. Not all reactions involve reactants in the same state of matter. Heterogeneous reactions are reactions that take place between reactants in different phases. So some reactants might be solids while others are liquids, or solids and gases, or a liquid and a gas. Homogeneous reactions, though, take place between reactants in the same phase. So two reactants in the liquid phase or two reactants in the gas phase. In general, homogeneous reactions proceed more quickly. In the examples here, you can see in this heterogeneous reaction, this looks like solid, like tightly packed solid, and then a liquid or a gas. And then similarly, these are in the same state, either both liquid or both gas. If one reactant is solid and the other is aqueous, the particles in the aqueous phase move to and then collide with the particles in the solid to react with them. The reaction only takes place at the solid's surface. Here we have aqueous HCl, so that's the liquid you see, react with a solid piece of magnesium ribbon. You can see the ribbon here. The H+ ions from the acid collide with the Mg atoms in the strip. So only the H+ ions can move, the magnesium can't move, and so they move to the surface of the ribbon to react with the magnesium. Bubbles form at the surface of the magnesium and then travel up through the liquid, which you can see here bubbling up. While it looks like the reaction is happening throughout the solution, it is only happening at the surface of the solid magnesium, and then the gas is evolving and bubbling up through the solution. Next, let's talk about how the concentration of the reactants might impact the reaction rate. As the concentration of reactants increases, so does the likelihood that the reactant molecules will collide. So we have a reaction here with this Bunsen burner, okay? So when you light the Bunsen burner, a flame is formed from the burning of the methane gas provided to the Bunsen burner. And so the reaction here is the reaction of methane with oxygen, the combustion of methane in the presence of oxygen on the Bunsen burner. The products of that reaction are carbon dioxide and water gas. So if I move from left to right, this is the same reaction occurring. But what's happening to the color of the flame, you can see it's changing from this yellow to orange to this purple and white to this blue and then this clear white flame. So what's happening as we go from left to right is that more air is being mixed with the methane. What does that do? That provides an increase in one of the reactants, an increase in the oxygen present, right? And so that increases the rate of combustion and the flame gets bluer because more energy is released and blue light has more energy than red light. So in this case of the Bunsen burner, there's a way to adjust the amount of air being introduced through this air hole. And as more air is introduced, the concentration of this reactant, oxygen, increases, which increases the rate at which this reaction occurs. That's demonstrated by the increased release in energy in the form of light. So we see a darker color of light. Let's next discuss the effect of temperature. Increasing the temperature means that more particles will collide with enough energy for the reaction to proceed. So an important definition here is that of activation energy. The activation energy is the minimum energy required for a collision between particles to result in a reaction. It's sometimes also referred to as the energy barrier, since it can be considered a hurdle that the reaction must overcome. Without overcoming that energy barrier, the reaction will not occur. Presence of a catalyst. Catalysts are substances that speed up reactions by changing the pathway of the reaction. The change in pathway results in the reduction in the amount of energy required to have productive collisions. In other words, catalysts reduce the activation energy. Catalysts are unchanged by the reactions they facilitate. Platinum-based alloys are commonly used as catalysts. You can see an example here of this solid platinum-based alloy being used as a catalyst where this molecule utilizes the catalyst here to then more quickly produce the product. Car catalytic converters are examples. They use platinum-based alloys to convert toxic gases into water and carbon dioxide in the exhaust from our cars. Surface area. Reactions with solid reactants proceed faster as their surface area increases. More surface area allows for more collisions between particles. A steel bar will not ignite if exposed to a flame. If I just have a piece of steel and I try to light it, nothing happens. However, if I have a pad of steel wool, it will ignite and burn quickly due to its texture, which exposes more surface area for more collisions to occur. There's a link to a video here you can click to watch the burning of that steel wool happen. Orientation. Atoms or molecules can only react if they collide with the proper orientation. So let's look at the reaction we have seen here. In this reaction, the single chlorine atom on the left collides with the chlorine atom in this NOCl molecule. So NO, and then in green is Cl. If the single chlorine atom were to instead collide with the nitrogen or the oxygen, the products would not be formed. The collision has to be between the two chlorine atoms to form this intermediate known as an activated complex. And then finally we get our products, the chlorine molecule and nitrogen monoxide, NO. When a collision occurs with the correct orientation and enough energy, an intermediate particle is formed known as the activated complex. So here's the intermediate right here. The activated complex is highly unstable. Without any further input of energy, the activated complex will transform into the product or products because it's energetically unstable. So it will quickly rearrange and form the products. All right, so let's use these model diagrams to discuss this idea of collision theory more visually than we did in a previous slide. So two molecules collide in this case with insufficient energy to cause a reaction. So remember, in order for a reaction to occur, we need particles to collide with not only enough energy, but in the right orientation. So in this first case, we're saying the molecules collide with insufficient or not enough energy to cause a reaction. If that happens, if they collide, but there's not enough energy for the reaction to occur, they just bounce off of each other and go in opposite directions. The arrows indicate the speed and energy of each of the molecules, which are composed in this case of chlorine in green, nitrogen in blue, and oxygen in red. In the second case, the two molecules collide with sufficient energy and correct orientation to cause a reaction. So you can see the two molecules collide with sufficient energy and correct orientation. We form an activated complex as an intermediate step, and then the reaction products separate. You can see in this case, one chlorine is now attached to this molecule and the other is on its own. The arrows again indicate the speed and energy of each of the molecules, which is composed of chlorine, nitrogen, and oxygen. So if you compare the size of these arrows to those on the previous slide, you'll see on the previous slide the arrows were smaller because in that case there was not enough energy for the reaction to occur. In this last case, the two molecules collide with sufficient energy but incorrect orientation. So you can see that the molecules are flipped or rotated from the previous slide. This one is vertical, and this one's flipped a full 180 degrees. And so now the molecules are colliding with sufficient energy, but incorrect orientation. So when they collide, they don't form an activated complex. They just bounce off each other and separate without reacting. And again, the arrows indicate the speed and energy of each of the molecules, composed of chlorine in green, nitrogen in blue, and oxygen in red. All of these factors come together mathematically in the rate constant. The rate constant, which is symbolized by this lowercase k, describes the relationship between the concentration of reactants and the rate of the reaction. The Arrhenius equation, which is shown below and we'll discuss in just a second, describes the mathematical relationship between the rate constant and the conditions that were discussed in the previous slides. Orientation, frequency of collisions, activation energy, and the temperature all have an impact on the value of the rate constant. So the rate constant K is equal to P, which is the orientation factor, times Z, which is the frequency factor, times, this is a constant, E, known as Euler's number. For you, though, you can just find this E, this exponential value E, on your calculator. And we raise E to the power of negative E sub A, which is the activation energy, divided by this product R times T, where R is the gas constant, and we've got to be careful about units in joules, and T is the temperature in Kelvin. The larger the rate constant, the larger the value of K, the faster the reaction proceeds. So the rate constant is directly proportional to the orientation P and the frequency Z factors. So when the orientation factor is large or the frequency factor is large, then the rate constant is large and the reaction proceeds more quickly. So what that means is a higher P or a higher Z means that the collisions are happening with the correct orientation and a very high frequency, okay? Since there's a negative sign in front of this exponent, this is negative EA over RT, if the activation energy is large, the larger this activation energy, the smaller the rate constant. So those are indirectly proportional. So if the activation energy E sub A is large, the rate constant is small, and the reaction proceeds more slowly. Similarly, because temperature is in the bottom of this negative exponent, if the temperature is high, the rate constant is large. So those are directly proportional, and the reaction proceeds more quickly.